Hello, Longhorns. Today we're going to dive into a new section. We've been working with work, potential energy, kinetic energy, mechanical energy, and power. We've been talking about the way that energy is able to transform from one version to the other or from one form to the other. And we're going to explore a little bit more into that topic as well. But next we're going to move into a topic as to how does energy move from one place to the other. We're looking today at lesson number 12, coming from pages 366 through 379. We're going to take a look at the wave. When you hear the word wave, you're probably thinking about ocean waves, and we'll talk about those as well. But I want to introduce you into some major vocabulary that you will hear several times over the next upcoming weeks. So today's lecture is going to be on simple harmonic motion. What does a wave look like when we're asked to put it on paper? Well, we're going to do a little simple definitions here. So anytime we have an object that's going back and forth, it's going to have simple harmonic motion. We've talked a lot about the pendulum, and that was the very first picture that you saw on slide number 1. Think of a mass like a ball or a tennis ball or steel ball that's hanging from a cable or cord, and it's rocking back and forth. We've used this example to talk about potential energy and kinetic energy. And we're going to see how would this look if we happened to add a pencil at the end and had a moving sheet of paper. We would see that as the pendulum was moving back and forth, it was also creating the outline of a wave. Now, when talking about harmonic motion, we're talking about our pendulum. We're also going to talk about springs. What happens when an object is in a position, the spring is then stretched, and what brings it back to its original state. So that elasticity, being able to stretch and to come back. We'll look at that as well. Now, we're going to call that a restoring force. To restore something means that it was once in a beautiful condition. It was in a good position. It was then moved, and now you want to move it back. There's an equation for that in physics. Mathematically speaking, it's known as Hooke's law. We're going to have capital F for force equals negative kx. And this is your Hooke's law. It's going to explain how much force is needed to bring the object back to where it started. And once again, that's known as your restoring force. The units for this are going to be a Newton meter. Whenever you hear Newton or see a capital N, we always think of force. And of course, our meter is going to be tied to our x4 distance. We'll learn in a couple of slides the negative K is known as a constant as well. So here's an example. We have a load of 45 newtons that is attached to a spring that is hanging vertically, stretches the spring 0.14 meters. What is the spring constant? So 45 newtons is your force. That number is familiar. The spring has been stretched. Kind of think of a slinky. So it's been stretched for 0.14 meters. And we're now looking for the spring constant. And remember that spring constant was represented by a lowercase k. You may be asking yourself, where does the negative come from in Hooke's law? That negative simply tells me about direction. We're talking about displacement, even though they're going to call it distance interchangeably in your book. But displacement is a vector. It has both magnitude and it also gives you direction. So let's go ahead and investigate this problem a little bit more. I do want you to continue to use the guess method. Though our equations are going to start out very small, eventually our numbers will get really big, really small, and this will help us keep up with our units. So let's see. We have a load of 45 newtons. First step is going to be my given, making sure we label. So F is equal to 45 newtons. It's attached to a spring that is hanging vertically. Now, vertical and horizontal are going to be key. Think about the horizon when the sun is coming over the horizon. Your horizon will go from east to west or from left to right if it's horizontal. Anytime it's vertical, I want you to think north to south or up and down. All right? So we're hanging vertically from a spring that's been stretched 0.14 meters. So we have 0.14 meters, and that's going to be represented by your K. And we're looking for your spring constant. So our unknown is going to be a lowercase k. Our equation that we just learned is F equals negative KX. For your substitution step, I want you to stop and ask yourself, is there anything that we need to convert? Units have always been an ongoing issue. It's usually the number one thing that we forget to look at. For this upcoming unit, and of course for the quiz and the test, you have to pay attention to units or your number will be a little bit off. We have newtons for force. We also have meters for displacement, so we should be pretty good. So for our substitution step, there is nothing. I think from here, we should be ready to solve. And we're going to plug in our numbers. Our force is 45 newtons. We're looking for Planck's or spring constant, and then our x will be 0.14 meters. Whatever number is next to your unknown has to move. So we know that 0.14 is next to our k. We want to divide both sides by 0.14. And we're using different colors so you're able to see it. Whatever I do to one side, I have to be sure to do to the other. You'll always have the question, what's going to happen here? We have the same number on the top and the bottom. So these two numbers are going to cancel out. And that's going to leave my k to the side. Here, we simply need to divide. So grab your device, and let's see what number we come out with. 45 divided by 0.14 will give you 321.43. And we know that our unit is a Newton meter there. Now, the other thing is when it comes to your K, your spring constant, you want to be careful where you round. Sometimes we round a little bit too much and we're not necessarily paying attention to exactly what's going on there. So your answer should be 321.43. Most of your problems are going to be very straightforward. They would normally ask you to only calculate force. So either force or spring constant are the two variables that you want to pay attention to. Now, let's go back to our pendulum a little bit. And these questions you will see really, really often. If you think about it, if we're at the very bottom, this is our lowest point. And if we're moving, this is where your kinetic energy is the highest. As it rocks from left or to the right, that's where your potential energy will increase, your kinetic energy is going to decrease. Now, we have a frictionless point, and we talked about friction. It's always opposite motion. That's going all the way back to last semester when we did Newton's laws. And if they ever talk about a bob, the bob is